Good evening, everybody. Good evening and welcome to BrisScience on this lovely, chilly, rainy Brisbane night. And yet we have a packed house. Thank you all for coming out. What a credit to our speaker. I am your MC for this evening, Joel Gilmore, and this is BrisScience, Brisbane's series of free monthly lectures on science brought to you by the University of Queensland, where we aim to bring not just the best scientists, but also the best communicators to share their research with Brisbane and all of our audience online. I would like to start by acknowledging the traditional owners of the land on which we're meeting tonight and everyone watching on YouTube later, and pay my respect to elders past and present. And we acknowledge that our actions around the country do have impact on the traditional lands and waters of the First Nations people, and we try and be respectful and think about that in every interaction that we take. So, a few bits of housekeeping first. This is, of course, we're going to have a talk, and you are going to need your phones to ask questions at the end of this talk, because we take questions using this amazing this amazing QR code here. So if you scan that QR code, you will get to our question page where you can ask questions throughout the talk, and there'll be a little bit of time at the end as well. But please put your phone on silent while you're doing that, because we would not like you to phone a friend during the presentation. Afterwards, we will have some food and drink outside. If you've been coming a while, you will notice we have now relocated the food to down the side alley here, just because the edge actually now stays open later than it used to. And while we would love to feed all of the students who are out there, there are some very hungry students. So just make your way down the side, and then you can sort of distribute yourself around afterwards. Okay. So last month, if you were here, we were talking about space and beyond. We were talking about asteroids and the very big. This month, we are pivoting a little to talk about the very small, heading down to the nanoscale. And we have a very special guest speaker tonight. We have Professor Helena Rubinsztein-Dunlop, AO, who is not just an eminent physicist, a director at the ARC Centre of Excellence in Engineered Quantum Systems, and also in the brand new Centre of Excellence in Quantum Biotechnology, with a slew of papers and a long history. But Helena, we would not be here tonight without her, because 18 years ago, Helena started BrisScience. Along with an amazing Jennifer Dodd, who worked at UQ as well. And we've been a little bit late inviting her to speak, but better late than never. And I should say, I wouldn't be here either, because Helena was a staunch supporter of my early science communication days, including buying me all the liquid nitrogen I could use. Absolutely none of which ever ended up in the UQ fountain. So tonight, though, Helena, rather than resting on her laurels, is charging ahead. Tonight, Helena is talking about using lasers as optical tweezers to manipulate matter at the smallest scale, and everything from precision medicine to possibly taking us back out into space. She is laser-focused, as always. Please welcome Helena Rubinsztein-Dunlop.
Thank you very much, Joe. It was an introduction and a half. I wonder whether I can do anything which will require... Anyway. Okay, so as Joe said, I will be talking to you about nanotechnology, but really with a little bit of a step out to bigger things. So we want to talk on one hand about nano and micromachines, driven by light. On the other hand, I want to talk to you a little bit at the very end of my talk about space sails, so solar sails. And these are rather big, but they have been proven that they work on nanoscale. So let's start my talk. So you can see here in this slide little things that move around. So they are pushed by light, but not only pushed by light, but as you can see, they rotate in the light. So we want to understand how that can happen. And then you have this sign there, which is sort of wiggly sign of OMG, which is not oh my God, but optical micromanipulation group, which is my group. And each little dot is a little micron-sized particle, which is being moved to where it is using laser light, very highly focused laser light, to make this picture. And you can see that they wiggle a little bit, and that's called Brownian motion, and we see how that happens as well. And then, the last but not least, is this lower thing here, a sphere, which is moving around and rotating quite fast. And again, this sphere is only 5 microns in size, and we can use light with specific properties to turn it around, and we'll try to understand how this is possible. So what I want to do today is to play with light and do impossible or possible, or impossible being possible, whatever you want to call it for. So as you can see here also, I have this funny figure here. This is, you might recognize, Einstein and Bose. Not quite. And these two figures are written using light, which is sculpted light of laser, which is formed into their faces, which was in-programmed. But this is not written only by light, but we use this light to harness atoms, individual atoms, to be in the image of their faces. So this is what we can play, how we can play with light. Okay, so as I said, what I want to tell you about is a little bit that light, it's all possible because light carries energy and momentum, and we'll look at that a little bit more in details, and then talk about optical tweezers and what we can do with them. And then optical tweezers, as I will tell you, is based upon the fact that actually light, we can show that light does carry momentum, and I'll tell you more about it, and therefore use it for certain purposes that when the linear momentum is transferred to our objects. But then I will look at other properties of light, and that it carries also angular momentum of light, so it not only pushes things, but it can turn things around, and look at the applications of that. And then we'll go to shaping light again to make Bose and Einstein and you and me and whatever of looking like in atoms, and look at the optically driven micromachines, metaspinners, and solar sails to end with. Okay, so I'm trying to start it. So the first question we can ask ourselves is, can light exert force on objects? And we know that light carries energy, and that's very simple. If it's a sunny day, not like rainy day today, but if it's sunny day outside in the middle of Brisbane summer, and we go outside, we feel, and the sun is falling on us, we can feel that our body is getting hotter. So that's the sign of the light carrying energy, okay? So that's pretty simple. And that energy can be expressed as depending upon this constant, which is called Planck's constant, times speed of light divided by the color of light, okay? And that was described by Einstein in early 20th century. And what about momentum? Okay, so what is momentum? If the light carries momentum, that it would mean that if I'm standing outside in a sunny day and feel heat coming onto my body being heated, then if it carries momentum, then it would mean that I should be pushed by light backwards. But I'm not. We know that if I stand in the sunny day, I don't feel any push. Well, I don't feel any push because I'm so heavy and so big that that momentum that the light carries is very small. So let us look at it. So momentum of light can be expressed as the energy divided by the speed of light, okay? But speed of light is very large. It's 3 × 10⁸ meter per second. So this momentum will be very small. Okay, so here are the constants that the symbols that we are using here. So this Planck's constant is something which is as small as 10 to minus 34, okay? And the wavelength of light is of the order of 10 to minus 10. So you can see that if we look at the momentum, if we look at the momentum, then this will be a very, very small number. And this is why we cannot feel being pushed by the light. Okay, so let us look at an example. So when the light is absorbed or reflected by an object, momentum is, as we said, transferred to the object. So that transfer of change of the momentum will be change in energy divided by the speed of light. Because P, the momentum, was energy divided by light, so divided by the speed of light. So if I'm looking at the change in the momentum, that's the change in energy divided by the speed of light. And what is the force acting on it? Well, the force acting on it will be equal to the change of the momentum divided by time. And we can also express it as, so there's my force acting on this body here with cross-sectional area of A. So the force acting on it will be intensity of light times this cross-sectional area divided by C. All right, so example now. So let us have a person lying down in bright sunlight, and the average power per unit area delivered by the sunlight on the Earth will be 0.2 watt per square meter. So then we assume that the surface of this person is 40 centimeters times 1.65 meters. And so we calculate this force which is acting on that body, and we can see that it's about 10 to minus 10 newtons. So it's not large force, but it is a force, right? Okay, so let us look at comparing it with how much force we need to lift a person which weighs about 60 kilograms. And that force will be equal, according to Newton's second law, it will equal to m times A. So that is mass times, what am I talking about? Yes, times mass times gravitational acceleration. So it will be around 600 newtons. So this is 500 times 10 to minus 2 plus to 10 orders of magnitude larger than the force acting on us when we're lying in the sun. So 10 orders of magnitude difference. So how much force is needed to move a tiny thing around, okay? So I take a biological cell. It's approximately 10 to minus 6 cubic meters, and its mass 10 to minus 15 kilograms. I calculate the force, and it's 10 to minus 7 or 8, around 8 times 10 to minus 14 Newton. So this is orders and orders of magnitude, smaller force. So the question is, how can we get that force to be measurable and see results of it? And the result of this force on small particles has been known for a very long time, starting with Kepler, going then to Maxwell, going to Kelvin, and et cetera, and you can see it here when we look at the tail of a comet. So this is a comet traveling around the sun, and you can see it's being, the sunlight is coming onto the tail of the comet. The tail of the comet is made of tiniest little particles, and we can see that this tail is turning away from the sun. So here is the simulation that my colleague has prepared for us. So here is my comet, and it's going around the sun. So the white blob is my sun, and you can see how the tail is behaving when the comet is traveling in its orbit. And if we look very carefully, we can see that it's turning away from the sun. So it's being pushed by what we call radiation pressure. Those little particles that the tail is made out of is being pushed by radiation pressure away from the sun. So this is what we were looking at. So I have my sun, and I have the comet going around in the orbit, and it has two tails. One is made out of gas particles, and the other one of the little tiny dust particles. And you can see that those tails are moving away from the sun. The dust tail is moving away from the sun, which means that there is a pushing force on those particles that is visible and probably measurable. And this is the observation that was made in 1997. And you can see the two tails, the particle tail and the dust tail. And you can see that one, because the gas particles are much lighter, they are further away from the sun. And then you have the tail of the particles, which is going away from the sun as well. So we have evidence of the momentum being transferred to these particles. Okay, so let us look at the example again. So we did say that average light intensity from the sun on the Earth will be around 0.2 watt per square meter. And we said that that was not even enough to move a microscopic particle. It was almost enough, but not sufficiently. So we need several orders of magnitude increase in intensity. So if I were to move my particles very close to the sun, intensity is diminishing with it's inversely proportional to the square of the distance. So therefore, if I'm very close to the sun, then I will have this intensity much larger, and so I would be able to work with it and have a little bit more momentum transferred. But I need several orders of magnitude to increase the intensity somehow. So how can I do it if I'm not flying towards the sun? I'm doing it here on Earth. So I can do it using optical tweezers. So now I want to tell you what optical tweezers does. I take laser light, like this, and I put it through very high numerical aperture objective. So I make it to tiniest little spot. And that's what you can see here. So it's my laser light coming in, and it comes to the minute spot here in the middle. So these are intensity profiles, and the yellow arrows are showing what are the forces acting on the particle in that laser field. So again, what we have done is to get the intensity of the light that I'm illuminating my particle with to the tiniest spot, so that means that it's much more intensity in that spot, and then I'm illuminating my particle with that. And here is the, if we go back, will it work? No. Okay, here it goes. So you can see the simulation of what is happening. My particle is coming, doesn't want to do it. Okay, here we go. My particle is going into highly focused laser light, and you can see that there is scattering of light, which is coming at the bottom of this cell here. And if I am able to measure how this light is being scattered, I can tell you what's happening with this particle, where it is placed, what are the forces acting on it, and from which side it approached the trap. So I'm able to trap the particle three-dimensionally and then calculate what sort of forces are acting on it, and also what are the displacement that those forces are causing. So here is an experiment done. So I have my micron-sized particle, which went into the very tight trap, and I am moving my trap, and I can move it in X and Y direction, and the particle stays trapped. And I can follow its movement, and I can measure the forces acting on it. And when you see these particles here, these are not trapped, and they wiggle in the liquid. This is all done in liquid. And as they are wiggling, they are experiencing Brownian motion. And my trapped particle also experiences Brownian motion, but it's much smaller than it is when it's not trapped. So I can use that to characterize my trap. So this is as much mathematics as I will be using today. So I characterize my trap as being a harmonic oscillator. So I set it in a potential and, of light, and the particle is wiggling. What you see here are the traces, how the particle has moved in time. And I can analyze how this is happening and plot it. So I can plot the mean square displacement of the particle as a function of time. So here you can see the traces, and I analyze it, and I can then characterize my trap in details, in minute details, and calculate what's happening in that trap. And what it gives me is to see how strong the trap is, the trap stiffness can be determined for this trap, and it will depend upon the role of frequency, which we have on this graph at this point, and then it will be depending upon the viscosity of the liquid in which we are doing the experiments, and at the size of the particle that we are trapping. And if I can analyze all that, I can use it in different ways. I can use it for characterizing my particle. I can use it for characterizing the liquid that the particle is in, and for many other things. And I would like to show you a few examples of how it can be used. So typical experiment is very simple. I won't go to very big details here, but we basically need a laser, and then we have clever instrumentation that allows us to bring light to be of any shape and form that we want to deal with, and I will show you a little bit more of that later. Then we have few lenses and devices that will let me put the light in the best possible way to my objective, and then I can look in the camera or other detector system on what is happening in that trap. And what you saw in the previous transparency was what we were doing in one of the detectors. Okay, so we have the setup. So then, instead of having just one trap, I can have many traps, okay? So I can use these clever things that are called spatial light modulators or digital micromirror devices to create 4 traps instead of 1, and then trap things into them. So let's see what happens. So I have dancing cubes here. So I have 4 traps, and I move them in 3 dimensions, and you can see that I'm holding them trapped in 3 dimensions to my liking. And now let's have a little bit of fun. We have Tetris here. Is the sound coming? So there you go. So this is how controllable the trap can be. We can play all sorts of games with it that we want. We can stop it now. Now, how do I stop it? Okay, and here is another example, another fun one. So this is manipulating each individual trap in time, and then it shows you how well we can manipulate the particles and have them do what we want them to do, to beautiful music. All right, but they were nice examples, but they didn't teach us anything. So what can we use the optical tweezers for? We can use them for studies of complex biological systems, and in fact, Joel mentioned that I'm part of the Center for Quantum Biotechnology, where we are trying to develop new methods based on quantum light for investigations of complex biological systems. And what I'm showing you here is that we can use optical tweezers, for example, with very special light to study single molecules. We can use them to study cells, and we can use them to study a whole brain. And I will give you a few examples of what we do with optical tweezers. So here is one example. Okay, so I want to push again. So we want to study molecular motors, and this is one of the molecular motors. It's kinesin motor, which is going on a myosin here. And people want to understand how the stepping of the motor takes place, what are the forces involved, and etc. So in order to do that, what we can do is to use optical tweezers for looking at the stepping of this molecular motor. And so what is done here is basically, here is what you saw before, the myosin, and then there is this molecular motor here, and I attach some marker on it, and attach it to a humongous bead that I had before, a few microns in size, and this bead is being trapped, okay? But if this myosin motor is, a kinesin motor is stepping, like a drunken sailor or whatever it does, then it moves my trap a little bit. And if I can now measure the movement of this trap in a very precise way, I can tell you how this walking of the motor is taking place, what forces are involved, how big are the steps, etc., etc. So this is what is done here. So this is how the experiment is done. We attach one side of this motor to this humongous now bead, and we put it in optical tweezers, and then as it steps forward, we measure what happens in the tweezers. So this is the measurement. It's a very old measurement. It started in 2011 in the group of Christopher Schmidt. And what he did is exactly what I described for you. He had his kinesin motor on microtubule, and then on the other side, there is DNA linker, and then the biotin streptavidin glue that puts it onto the trapped bead. And then as the stepping takes place, this bead is moving in and out, and then we can measure in time position of this trapped bead and see forces being involved and characterize in minute details what is happening with this motor stepping ahead. And then this type of measurements has been done throughout the times, and here is the review from Carlos Bustamante's group from 2021, where they are showing what sort of combinations of different methods you can use for looking at those molecular motors in details. So you can use the method that I was showing you before, that you have optical tweezers, you measure the force that is happening when the extension is happening, and in order to get the extension happening, what you can see is the motor moving, or you can move the slide and see what happens when this extension takes place. And you can also use tweezers in combination with a pipette. So you grab another bead into the pipette, and then you look at the movement. Again, extension takes place, this bead wiggles, and we measure the wiggles of that bead. Another thing you can do is you can have double tweezers and measure the extension. You can combine this thing with fluorescence, epifluorescence microscopy. You can combine it with another type of microscopy, which is total internal reflection, and confocal microscopy, etc., etc. Why I'm showing you this is that it's a very, very big field where people are able to study single molecules' behavior in very, very precise way. And what our physical method bring is that we can measure forces and displacement and give it a number. So this is quantitative measurement that our methods allow. And the last but not least is that you can also do it in angular optical tweezers that I will tell you a little bit more about. I mentioned before that you can have a transfer of angular momentum of light to particles, and that has been used in these studies in Michelle Wang's group in Cornell, where she was looking at uncoiling of DNA molecule by using these rotating optical tweezers. All right, so another example that I want to enchant you with is that you can cheat the fish that it's moving by using optical tweezers. So why is it interesting? I mean, we had great fun doing it, but the work was done by Itia Favre-Boul in our lab. And so what this study was all about is, this is a study about the functioning of the brain. So what we wanted to study is the vestibular system of the zebrafish. And vestibular system means movement and hearing. And this is important. Why it's done in zebrafish is because zebrafish brain is minute in comparison with human brain, but zebrafish brain is very good model of mammalian brain. So therefore studying that model gives us notion about how our brain functions, so understanding that model can be translated to full human brain. So what we studied here was, as I said, a vestibular system. So we have stones in our ears that make us have balance, and if those stones, which are called, what are they called? That escapes me now at the moment. Anyway, so there are stones which are birefringent, and if they are not functioning very well, what happens? We lose balance, and so they provide us with balance. So, and the way they provide us with balance, of course, is that if we move one way, then there is a signal going through a neuronal network to our brain to tell us that we have to move in opposite direction or whatever. So what we did with optical tweezers is to cheat the fish that it's being moved, and so we wiggle those stones. They're called otoliths, and we wiggle the stones, and the fish is thinking that something is attacking it, and it's starting to move, and then we follow it by looking at how it reacts with its eyes and its tail, and also how the neuronal network is working. So let me show you that. Okay, so here's my zebrafish, and those red dots are showing where I'm applying optical force, and you can see that it's moving its tail, and I can follow the movement of the tail here in this graph and see what is happening when I'm interrogating one stone on one side and then the other stone on the other side, and then both stones either in opposite direction or in the same direction, and all that sort of stuff, by exerting this minute force. You remember that the force was only of the order of piconewtons, so 10 to minus 12 newtons. Okay, so then this is the modeling of it. So is it moving or not? No? Okay, so I'm interrogating one stone, and the fish is reacting, and I can measure it. So this is what we see in the graphs. And then we can go to the next one, and I'm going to the other stone, and it will move the tail the other way, and I can measure exactly how much it moves. And then I can go to both, interrogating them in the same direction and see what happens with the tail, etc., and analyze all that, and happily understand the movement of the fish. And then I can follow it by looking at the signaling of the brain as it is happening. So what you are seeing here is that I'm following the neurons which were reacting to this moving of the stones, otoliths, and then we can see that the pathway for when I'm moving one side of the stone versus the other side is different. And so we can observe it, and I don't know, it doesn't play, but that was done here in 3 dimensions. We can look at the total movement of the fish and which neurons are reacting. Okay, so that was a nice example of biological systems that we have been studying and other people are studying. But as I mentioned at the very beginning, it's not only so that we can transfer linear momentum of light to the particle, we can to objects. We can also transfer angular momentum of light. What I mean by that is that the light can have spin angular momentum. What it means is that my electric field vector is propagating in space and describing a circle. And that's circularly polarized light, either left-handed or right-handed circularly polarized light. And such circularly polarized light carries plus minus h bar per photon of spin angular momentum, Remember what h was? H was Planck's constant, and it was really very small. It was 6.626 times 10 to minus 34 joules second. So we are not talking about great momentum, but it's enough to turn things around. So here I'm transferring spin angular momentum to calcite crystal, and you can see that it's spinning because I have to conserve spin angular momentum, and when the light is falling on it and it has spin angular momentum, then it is being absorbed by the particle, and then the answer is that it's rotating in opposite sense to what the light was carrying. And here is another type of spinning. So this is also calcium carbonate, but this time spherical particle, and it's difficult to see that it's spinning because we were able to make it very smoothly spherical, but you can see that the liquid around is moving. So I should point out here that it's still this spin angular momentum light. I still have my Gaussian beam, which looks like this pointer, a little dot, but within it we have spin angular momentum of plus minus h bar per photon. Okay, well, that was another thing I wanted to mention, and it is that here at the top we also see another type of angular momentum. It's called orbital angular momentum, and I'll tell you a little bit more about it as well. So these beams look like donuts, but what is characteristic for them, we call them optical vortex beams or singular beams or Gauss-Lagrange beams of light, and they carry plus minus L times h bar per photon of orbital angular momentum. But this is a little bit different to spin angular momentum. This is this is the pointing vector of the light is going in a circle, and it looks like this. And so it carries orbital angular momentum, okay? And this L here, where are we? L can be very large. Starting from 1 or from 0, that will be Gaussian beam, and then we'll be back to Gaussian beam. But if it is higher, then there is more orbital angular momentum that it can carry. So it is quite interesting because you can see that orbital angular momentum can be quite high, while spin angular momentum can be only 1 times h bar per photon, okay? So I can transfer much more orbital angular momentum and do something about it. Okay, so going back to spin angular momentum, what can I do about it, with it, and how can I use it? So I'm using it as a measure of the liquid in which I'm rotating my particle. So what I'm doing here is that I've sent circularly polarized light, so this light that carries spin angular momentum, onto a very special material, which is so-called birefringent. So it means that the light which is traveling in one direction in this material travels with different speed to the light which is traveling in this direction. And when they meet, those two components meet on the output of this plate, then I'm getting different polarization of light. And so if I'm lucky enough to build this plate of certain very specific thickness, which in this case would be wavelength of light, so the color of light divided by 4, then I will get from circularly polarized light, I'll get linearly polarized light. So I can use it for measurement of, if I can measure how much this polarization is changing, that will give me information, and how much the rotation is taking place, that will give me information about the environment in which this rotation takes place. So what we are doing here, a little bit of equations here. I have optically applied torque, but I also have viscous drag torque, and then these should be equal to each other. So that means that eventually I'm ending up with this equation that looks horrible, but what it says is that if I can measure the change in polarization of light, so how the light looked here versus like it looked here, and that's not very difficult measurement, and I know the power of my laser, and I know the size of my particle, and I know how fast this plate will rotate, and I know the wavelength of light, then I can determine viscosity of the liquid in which it is all happening. So here is the experiment, and you can see this particle rotating here, and this particle is rotating in water, and we compare the results of our measurements with the handbook values, and it agrees within 3%. So that's another example of how you can use optical tweezers. But you're rotating optical tweezers at that. But you also can use it in other experiments, very interesting experiments done in Professor Michael Burns' lab in California. So these are our rotating vaterides, our rotating particles. They are put on each side of a neuron or axon, and then they are being rotated in opposite sense. And what we are observing is how this axon is growing, how it's moving with time when this rotation takes place. And then it helps us determine what sort of forces are involved, on what sort of fluid, microfluidic flow is being generated, and how strong it has to be for the neuron, for this axon to grow in a particular direction, and how fast it will grow. So we're looking at the behavior of those axons in time. So that's another example. And another example of applications of that sort of technology is that we can use it for understanding certain processes in biology which are poorly understood up to now. And one of those processes is macropinocytosis. And what it is that our cells have to nourish themselves. So they build this. Now let me see whether it will work. Yeah. So the cell is building such ruffles on its membrane and engulfs material that it will be nourishing itself with. And that material goes into the cell, and then it is distributed. Then the macropinosome is being built. So these ruffles close on themselves, and they are going into the cell, and then they build macropinosomes, and then they redistribute the nourishment by shrinking and letting the stuff out, and then maturation takes place, and then we can see what's happening with the liquid inside those macropinosomes. So we are cheating the cell again here. We are giving it our rotating vaterides, rotating particles that I can rotate with my circularly polarized light. The cell eats them up, closes on itself, it's inside, and now I can measure how the environment of the cell changes as the nourishment is being distributed around the cell. And so we can see it in more details here. So this is what we have done. The cell has eaten up our micropinosome, and then it's inside the cell. I put my optical tweezers on, I rotate it, and I look at the behavior of this particle. And here is the result of the measurement. So you can see that I'm inside a living cell. So this is a macrophage cell, and it's staying alive. I haven't killed it or anything. And then the particle is rotating very fast in it, and I can measure that rotation. I can measure the change in polarization, and therefore I can tell you a lot about the whole cell behavior, macropinosome behavior within that cell. Now, I told you that we can also have orbital angular momentum, so momentum that has to do with the wavefront describing a circle. And we did say that the light then looks like a donut, but it's not just flat donut, but the light is rotating inside that donut. And the way to produce them, I will show you here, so we can produce them with different charges. So you remember that orbital angular momentum carried L times h bar per photon of orbital angular momentum, and L can have different values. So if L is 0, then it's my Gaussian beam. If L is 1, then I have this little donut, and L2, bigger donut, and bigger and bigger and bigger. But you can see also that the light, the intensity of the donut, donutty part around is shrinking and getting narrower and narrower, but there are more orbital angular momentum being transferred. So the way we produce this orbital angular momentum beam is very simple. Namely, we take diffraction grating. So we have a way of drawing diffraction grating at certain distances between these parts of it. And then instead of just having simple diffraction grating as you have here in the bottom, which will send the light to different orders, what we are doing is we're taking a little fork in the middle here, and then when we put our light on top of that, we'll create orbital angular momentum beam of the outcome, and this is how it looks in practice. So I have a Gaussian beam. I put it, so this has L equals 0. I put it on this diffraction grating with the fork on it, and depending how many parts of the fork we have here, we'll have a donut beam that has different special charges. So in this case, it's L equals plus or minus 3. And then we can use it for the rotation that I was describing before. So here is one example of it. Okay, so these are LG beams. One is, I think, 60. The outermost has L equals 60, and the inner one has L minus 30, and you can see that little particles are rotating around those beams in opposite directions, because one is plus and one is minus, and you might ask what is it good for, and that can be good for a lot of investigations of polymers and other things. So here is an example of our work on it. So here is a little dumbbell that I put in the orbital angular momentum beam, and you can see that I have built optically driven micromachine. And what it is good for is another story, but we have had good fun with it, so I will show you examples of it later. Okay, so now building micromachines. So previous transparency showed you a dumbbell. So this was just, I took two little particles that I had before in my beam, one before, and then I just clumped them together, and they are sticky, so they stuck together, and I got my dumbbell. But what if I want to build a sophisticated micromachine? So in order to do that, we use another technique. And this is called two-photon photopolymerization. This is all done on nano and micro scale. So I take highly focused laser beam, which has very, very high intensity, and I introduce two-photon transition in my material, in my polymer. What it means is that I pile photons up on each other, and they give me the proper frequency of light that will be absorbed by this particular material. And then when it is absorbed, chemistry happens and the material is hardened. And that focal spot is very, very small. So I can program it in such a way that I can move it so that it will be, this photopolymerization will be happening in 3 dimensions, one after another, and I can build different types of machines doing it. So not exactly a machine, but this bull is about 15 microns across, and you can see that it has minute little details, and that was done 23 years ago. So this technique today is commercial technique, and in actual fact, at UQ, we have a machine which does two-photon photopolymerization very well. So using that technique, we can use it to create rotors. We can create diffractive gratings, as I was showing you before. I can use it for whatever shapes I want. It's mind boggles what you can do. And then I can expose them to structured light and see what happens. So I can build micromachines to my liking. Okay, so here is one example of it. So I have, sorry, it didn't work. So here is an example of how we build those rotors. So this is offset cross, I'm sorry. I shouldn't have done this. Okay, so here is photopolymerization in action, and I'm building something that I have planned how I want it to look, and there is the electron micrograph of how well we have decided we're able to make it, and then I can rotate it in light. So I put it in the orbital angular momentum light, so with the hole in the middle, and eventually it will start rotating if I'm lucky. No? It just wanted me to have a break. Here we go. Here is the rotor, and it's in the orbital angular momentum beam, and it will just start rotating in a minute. It's very old film. I'm sorry about that. Here we go. Well, I think I convinced you that it can rotate. And now it's even better. Okay, so we can do even more. We can now construct optical diffractive elements. So I'm building something like this on my microscope slide, through which I put my Gaussian beam. But when the Gaussian beam is going through this type of structure, what the structure is enabling me to build orbital angular momentum beam on the output of it. And then I illuminate that light, which I produced. I illuminate my offset cross with it and see what happens. So that's what happens here. No. It doesn't want to go, but we'll force it to go. Okay, so here is my optical element. Now I'm putting it over my offset cross, and you can see that it's rotating very fast. So I'm using here just normal Gaussian beam, just a beam which looks like that, onto this structure. That structure then creates my orbital angular momentum beam on the output, and then I take my structure and rotate it in that beam. So this is optically driven micromachine. And then we can go further, and the idea here is to show you how clever we were. Namely, we are building something which we call paddle wheel rotor. So the idea behind it wasn't that stupid. What we wanted to do is to look at very flat cells. So the cells are on microscope slide, and they are very, very flat. And so if you want to interrogate them, for example, expose them to shear stress and see how they behave. That's very active investigation, type of investigations on cells. Then rotating something on top of them doesn't help you, but you want to rotate something on the side, so you create this optical paddle wheel. And what we did here is that, it shows you on the next slide, what we did is that we have double optical tweezers, which are sitting on the dumbbell there, on the sides, and then the paddle wheel is being rotated by another beam of light. And it pushes the paddle around and stably being trapped in the two tweezers, and then we look at the rotation. And here is the rotation. Okay, so you can imagine it turned around and put onto the cell and measuring what's happening with the cell. So these are our micromanipulation examples, and here is another one. So I can build whatever I want using my two-photon photopolymerization, and this is what I did here. I used this paddle wheel, and you can see that I trap it now in 4 tweezers. I thread it over the top of this stand here, and then I use orbital angular momentum beam to rotate it, and you can see that it's rotating here. This is the real picture of the rotor in Gauss-Laguerre beam of light, and you can see that this is done in Gauss-Laguerre beam of light that carries a lot of orbital angular momentum, because my L is now 20. So it's quite a lot of momentum. And we can play like that with whatever we want. So here are a few other examples. So that was my rotor that I was showing you before. Here I have orbital angular momentum beam that I also showed you before, little particles rotating in it and creating a flow, and this particle is going through the flow, so we can have microfluidic devices and study flows in those devices. And here is another example of what we do with our optical tweezers. We have a red blood cell, and we now have double tweezers, but no spheres in them, but just grabbing the cell in itself in 2 points and stretching it enables us to study elasticity of the cells. Okay, so this was showing you, all those examples were showing you how we can use transfer of momentum of light, be it linear momentum or angular momentum of light to particles, and enabling us studies of single molecules, cells, brain, and what have you. But you can use other ways of using strength of light to study other things and create other type of machines. So I want to tell you a little bit of work of Mikael Schell's group in Sweden, where they are looking at metaspinners. So this is a really clever method of using properties of light and what you can do with it. So the metaspinners are structures which are built on silica, and these structures are sort of diffraction grating, which are two diffraction gratings put in opposite direction to each other. And now I have just simple plain wave coming, so quite big, not focused laser light, which is coming onto these structures, and I want to see how they behave. Okay, and because the light is reflecting from them, okay, then it will reflect at certain direction, in one direction, because the grating is in one way, will direct this way, and in the other direction, in other part of it, it will be directed in this way, which will give it rotation, okay? So we can have rotation taking place. And I show you the rotation here, okay? Here we go. So I have left-handed metaspinner rotating in clockwise direction, and I can have right-handed metaspinner rotating in opposite direction, and you can see that I can control it very well. But then we can go further, and we can show you what happens in the liquid with it. So you can put trace particles in it and see how fast they rotate and what is happening there. Okay, and I will skip that, but convincing you that you can do a lot of fancy things, and these sort of things can be used in looking at pharmaceutical industry and other applications of molecular motors. We'll skip that, and I want to come to my last thing that I want to tell you about, and this is about solar sails. Okay, so for a very long time, solar sails were something of a science fiction stuff that people were thinking about, but today, where are we? Why is it doing this? Okay, but today there are several programs around the world where people are actually showing that you can have solar sails functioning very well. And what it is all about is that if we look at the rockets being shot onto the other planets, they have very high payload, and the fuel is needed and all that sort of stuff. It's very costly thing to be doing. Now, if we could do it only with light, that would be rather cheaper adventure. Maybe not cheaper, but at least nicer. Okay. Okay. So, Icarus. We all know the story of Icarus. So Icarus was son of a very clever man whose name was, escape me now, is Daedalus, and he built a labyrinth on Crete, where when the king of Crete wanted to get a king of Athens and keep him in the labyrinth, and the king wasn't supposed to escape from the labyrinth. However, the king escaped, and so then king of Crete was very angry with Daedalus and his son Icarus, and he put them into prison. And they didn't want to sit in prison, so Daedalus was very clever, and he devised wings for Icarus, that Icarus could escape from the prison. But those wings were made out of feathers and wax. So Icarus escaped, but he went very, very far towards the sun, and his wing burned. Because, of course, wax burns when it's very hot. So it wasn't a very good idea. However, they escaped. However, if you make the wings of special material that reflects the light very well, then you you expose it to sunlight or laser light, then you can propel those things in space. So the first experiment was done in the lab of Grover Schwarzlander, where he was showing that you can have a special type of materials and calculate what sort of thrust you can get at different angles, and show that you can accelerate those things in space and have a positive thrust. And so that was done many years ago. That was again 2011, and then many programs started. So one of them was Icarus program by a Japanese space agency, which shot out the spacecraft, which was powered by light in 2011 successfully. And the idea behind it is very simple, that if you have light incoming to a reflected surface, the light will reflect, and there will be force acting on it perpendicularly, and it will move and accelerate in space. And so these programs eventuated both, as I said, in US and in Europe and in Japan, and have been developing since, and are very successful. And here is the latest report from 2020, where Grover is showing also that what you can do is, instead of just having very highly reflective material, you can start playing with several things by combining this with a lot of knowledge of optics that we have and a lot of knowledge of materials. So we construct now instead diffraction gratings, which are done in such a way that you're not only pushing and accelerating the thing without control of its angle, but you also can control in which angle the force is acting. And using metamaterials with different refractive indices along the surface, you can propel these things very well in air. And in summary, I hope that I showed you that you have absolutely endless opportunities in using properties of light, and we can use them for new discoveries, new sensors and devices, and we can use them for single molecule detection. And with that, I just wanted to tell you that behind that work there are a lot of people, and here's my group, and I'm very thankful to be able to work with them, and thank you for your attention.
Amazing. What a tour de force through an incredible technology, and amazing seeing all these...
Just turn it off, don't know.
Oh. How musical themed question time. All right, we have questions coming in, but let's pop up the QR code if anyone else has more questions for Helena. I'm going to jump straight in. Katie would like to know, how many tweezers can you use at once, particularly on the same molecule?
Well, that's a very good question. It depends how big the molecule is. In principle, you can use as many tweezers as you want. But of course, light eventually is interacting, it will overlap with each other. So you are not winning very much. If the molecule is tiny, then using many tweezers doesn't help.
Great. Tim has a history question, which was, when and what was the first experimental evidence of the momentum of light?
Well, the first experiment of momentum of light, it was a long time ago. As far as spin angular momentum of light is concerned, It was 1936 by Beth, who was trying to show spin angular momentum transfer, and and it was partially successful.
Okay, Sarah, good question. Couldn't you just use an electron microscope or something similar to determine how proteins move? What is the benefit of optical tweezers over some of these other techniques that we have?
So the biggest advantage of optical tweezers is that it's non-contact method, and secondly, that I can use it on living samples. So I can use it on living cells. If you go to electron microscope, well, there are electron microscopes today which can work on frozen samples, but then you cannot do dynamical studies as you can do with optical tweezers.
On behalf of zebrafish everywhere, we thank you.
We didn't kill it.
No, yeah, it's good. It looked like a very happy little fish. Okay, I'm going to ask one more question, which is, this is mine. So you're here on the 18th anniversary of BrisScience. We bring you back in another 18 years.
I don't think so.
Oh, no. What are we going to be seeing? What would you be presenting on for optical tweezers then? Where do you think technology will be in another 18 years?
Well, you know, I'm not sure. I think it's very, very rich field. And I think that there's enormous amount of things that we can measure using those sort of methods, being transmission, being reflection, being optical tweezers of light. All the properties of light can be used, but I don't have a crystal ball to tell you where I will be in 18 years' time. I hope that there will be new physics. I hope that there will be new biology. And our big hope in our new Center of Excellence for Quantum Biotechnology is that if you marry those methods that I was describing for you today with quantum light, then it will lead to a lot of more developments that today are not possible. Because what quantum light will allow us to do, both in connection with optical tweezers, but for other imaging techniques, is that it will enable us to have better resolution and better specificity. And so new things will happen.
Amazing. Well, July 6, 2042, we'll look forward to seeing you all here to get that update. But for now, could you please join me in thanking the incredible Professor Rubinsztein-Dunlop. There you go.
Oh, thank you.
And please join us for some food and drinks out the side, and Helena would love to chat, I'm sure.